Hello and welcome to episode 18 of the Nord Search podcast. Today, I'm delighted to be joined by Tom Gowan, and I'm really excited to have this conversation. I actually met Tom at Energy Trading Week in London last week. We had a really interesting conversation about weather forecasting and AI, because that's what Tom is responsible for at Spire. He's director of weather prediction and AI. I know a lot of interest in weather forecasting right now. So, really happy for Tom to be on the episode. Thanks for joining me, Tom.
Yeah, no problem, Patrick. Happy to be here.
As we always do on the podcast, Tom, it'd be great if you could just give us an introduction to yourself and what you're doing at Spire.
Yeah, for sure. So my background is all kind of weather prediction, weather focused. I've had a deep interest in weather, as far back as I can remember. No idea where it started, but I've always just been obsessed with weather and everything about it in general. So I attended Penn State in the United States in Pennsylvania for my undergrad. It's a very popular school for undergraduate meteorology. And then I went straight to grad school at the University of Utah, because kind of while I was at Penn State, I got really interested in the actual prediction side, so the kind of technical side, how these models work, how you operate, how you do data simulation and make forecasts of weather. So I went to University of Utah, where I got my master's and PhD. My master's was focused more on kind of verification of these high resolution ensembles, so run it high enough grid spacing so that you can actually resolve kind of convective features. And then my PhD was focused more on these kind of more deeper scientific idealized large eddy simulations of lake effect snowfall. When I say large eddy simulation, that's really high resolution. So going down to 100 meters where you actually resolve turbulence. And my professor had a grant that focused on how these lake effect systems interact with downstream topography. So we actually from scratch had to kind of design these models and then run these very high resolution simulations to understand kind of the interactions with the lake and the actual physics of these systems and the snow they produce downstream. And this was generally focused on areas of the Great Lakes, United States, where lake effect snowfall is very common, and over the Sea of Japan, where those mountains actually experience some of the most snow in the world. And although it's sea effect snowfall, it's the same process as lake effect snowfall. And then towards the end of my PhD, that's when AI was starting to become kind of a more serious area of research within weather. And I did a kind of final project, the final chapter of my dissertation was focused on using generative adversarial networks to sort of increase the resolution of precipitation, specifically lake effect snowfall forecasts from the high resolution rapid refresh over model of the United States. So we went from kind of 3 kilometers to 1 kilometer using kind of AI techniques. And then as I was wrapping up, I heard about Spire Global, and there was actually a recruiter that reached out to me, and I started to research the company, and I was very interested. They're kind of this new space company that's been around about 10 years with 100 plus satellites in orbit and retrieving some proprietary weather data, which we'll talk about more further on this podcast. And the thing that really attracted me is they really seem to be at the bleeding edge on the science kind of and technology side within weather prediction. That's really where I wanted to go. I knew I wanted to go into industry, not continue on the academic path. And I felt like I could move much faster there and have much more impact within the field of weather. So I ended up joining Spire, and I've been there 3.5 years since. I've moved my way from kind of a numerical weather prediction scientist when I started. And then a couple of years ago, I became a team lead, leading a team that focused on our high resolution model development. And then within the last year, I became the director. And now I have kind of several teams under me focused on the entire pipeline. So the software engineering, the data simulation, modeling, machine learning, post-processing, and then AI. And that's where I'm at today.
Awesome. Awesome. Well, yeah, as I said, obviously from my side, I speak to clients in the power trading space, and I know there's so much interest in weather forecasting right now, especially with how quickly the advancements are being made in AI. So there's a lot that see significant value in terms of getting more accurate forecasting. So yeah, I'd be really interested to understand from your side, like just a little bit about like how Spire actually focus on weather forecasting, and then maybe lead on to like where AI has an involvement and where it is today, and where's it going. Basically, that'd be really
Yeah,
interesting.
yeah, definitely. So I'll start with kind of more of a background on the company of Spire and then lead into how that allows us to kind of differentiate on the weather prediction side and what we specifically do there.
Yeah.
So as I said in the last answer, Spire, it's a space company. It's kind of in this new space category. We were founded about 13 years ago, went public. What are we at? About 3 years ago, we went public on the New York Stock Exchange. So we're a publicly traded company. And at our core, we're a satellite company. We develop and manufacture everything we launch in-house. So we have offices all throughout the world, several in North America, several in Europe. But Glasgow, UK is our main spot where we actually develop and manufacture the satellites. And
That's interesting.
the majority of the satellites are for internal Spire use cases. So they collect data for different Spire business units, and then we have another division, which we call our space services division, which is where companies come to us and we build the satellites for them. Or if they have a sensor they want us to add on, we add that to the satellite, we build out their constellation, and then they just receive the data from the satellite. So we handle everything. We handle the building of the satellites, the launching, we have ground stations all throughout the world, and they just receive the data. So it kind of removes that insanely difficult layer of getting your products and your hardware into space, and they just receive data via an API, and it simplifies it for them. And then on the core data side of the company, we have three main business units. One is weather and climate, which I'm a part of, that does the weather prediction. And then we have a maritime business unit. So many of our satellites receive what's called AIS messages. That's on the maritime side. And these are messages that by law, all maritime ships need to be outputting, and we receive those with our satellites. And so we track all maritime ships globally and all kind of details about where they're going, what they're carrying, et cetera. And on the aviation side, we do the same thing with what's called ADSB messages. So that's kind of our data side on the maritime and aviation tracking. And then on the weather side, we have several data sets that we get and kind of merge into our products, with the key one being what's called radio occultation. So this is a technology where large GPS satellites they're outputting these GPS signals, and those are the ones going to your phone and telling you where you are on Earth. But some of these actually go through the atmosphere and then back out into space. And when they go through the atmosphere, there's a bend that occurs. And that bend is a function of temperature, pressure, and humidity. And then we catch those signals with our satellites, and we're able to back out profiles of temperature, pressure, and humidity. So we're essentially kind of doing what a weather balloon launched by a human on Earth, a very manually intensive and expensive process. We're sort of automating that. And we're getting up to about 8,000 profiles per day, evenly distributed over the world. So we're collecting data in very data sparse regions, say over the middle of the Atlantic or Pacific, where there's no balloons launched and we don't know what the weather is there. And we take all that data, we bring it into our models in performing a method what's called data assimilation. This is kind of the art of taking all weather observations and basically building them into a physically consistent grid, which can then be used into our weather models.
Yeah, so obviously you being a satellite company, so you fire your satellites up with SpaceX? Is that how it happens? And then
so the majority of our launches are on what's called SpaceX rideshare programs. So SpaceX is 90%, or that's an estimate of their launches, are launching Starlink or NASA missions, astronauts, things like that. But every so often they do a rideshare mission where they allow all these small satellite manufacturers to host their payloads and they go launch them. And that's what we're using with. We use Rocket Lab as well, and then a couple other providers.
That's super cool. It's funny how they call it rideshare, like you're just getting a taxi to space.
Yeah, exactly. That's the idea.
Okay, cool. So obviously that gives a nice overview of obviously what Spire does as a business. And I guess for obviously the listeners of this podcast is traders or trading focused. So can you give us an idea of how the business helps the trading industry?
Yeah, definitely. So I kind of ended that last story at the data that comes off our satellites on the weather side, radio occultation, and then we also have what's called GNSSR. These are the same signals, but when they reflect off water, we back out ocean winds, and they reflect off land, we back out soil moisture. So those are kind of our three key data sets. And then within my team, like I said, within the broader team, we have several teams that basically manage the entire weather prediction pipeline. That's sort of unique. Most companies aren't that deep in technical expertise. That's usually kind of reserved for more of the government entities like ECWF and NOAA. But within Spire, that's our focus, is we have deep expertise. There's roughly 15 or roughly 10 PhDs within my team. So really deep expertise in individual areas. So what we do is we take that data, we take very recent forecasts, usually from ECNWF. We apply our data to it as well as data from all other available sources. So everything we can get from NOAA and EUMETSAT, all satellite data, all ground observations, all weather balloons, and assimilate that to create the best possible image of the current state of the atmosphere. We then kick off 3 different models from that data. So at Spire, we run a high resolution model. It's a 3-kilometer resolution. And when you go into 3-kilometer, you're resolving, the finer details within the forecast. So individual thunderstorms, sea breezes, downslope winds, and these are all things that critically affect, individual cloud formation. These are all things that critically affect energy production, whether it's wind or solar, as well as demand, getting the temperatures correct. So we do high resolution forecasts over relatively large regions that cover all of the continents of the United States and all of Europe. And what's unique with these is we go all the way out to 6 days. So most other government entities are only going out to a maximum of 2 days. So beyond 2 days, you have to rely on a global model, which is very coarse and not providing a lot of the details necessary to make kind of informed trades, but for renewables, essentially. So what's unique is we go all the way out to 6 days. And we've done a lot of verification to kind of prove that our forecasts are state of the art. They provide value over kind of the best of the best that is out there. And that's why, a lot of our customers trust us. And then we also have a global forecast where we run, this one's at 9-kilometer this is a 12-kilometer resolution. So more standard resolution from the global side, but we go all the way out to 15 days. So kind of those medium range forecasts. That's what that global model is suited for, and for clients who aren't over kind of these heavily populated regions such as Europe and the continental of the United States. And then the AI side, we're doing subseasonal modeling, and I'll kind of wait to talk a bit more about that because I think that'll be a much more in-depth story there.
Yeah. Well, just before we get there, how can you get to 6 days if that's not really being done? If that's a bit of a USP for Spire, how can you do that?
So it's not easy, and it's very computationally expensive. So within Spire, like I said, we have our deep expertise extends beyond the science side. On the software engineering side, we have really world-class software engineers who have managed to run all these systems actually in the cloud, which is a bit unique. Most other providers are running on traditional kind of what you call a high-performance computing system, but we're doing this in the cloud where we can kind of scale, infinitely. So it's massive amount of compute. And there's many technical hurdles you kind of have to overcome to do this. Another aspect is, government providers aren't doing this because there is a lack of clarity on, is traditionally in the research, no one's really looked beyond the 2-day mark. And they've kind of decided, well, beyond 2 days, you're going to get the general placement of large scale systems incorrect. So why would you go to high resolution? But there's a lot of kind of emerging research in recent years that going out to the medium range at high resolution does provide benefits, especially on the convective scale when you care about knowing where individual thunderstorms are, squall lines. And of course, you want those fine details to make the proper trading decision. Is there going to be precipitation, clouds? When is the wind shift going to occur? From a global model, everything's kind of very smoothed out, and you don't know how sharp that wind gradient is necessarily going to be. So this is a bit exploratory what we're doing, but that's how we get our edge essentially. And, we didn't know the performance we were going to get by going out to 6 days, but we found that we provide significant value over the global forecast, such as ECNWF and GFS from that 2 to 6 day range. And we also find some evidence that we actually improve the large scale, because when you get out from the 2 to 6 day range, what happens at the small scale, so individual thunderstorms, large complexes, this is getting a bit more deep into the meteorology, but you get these large heat releases and moisture releases, and ultimately that will affect the placement of individual low pressure systems. And you're not able to resolve that at global modeling resolutions. So that's kind of another benefit. So it's the detail, and then it's also better predictions of the large scale atmospheric features.
Amazing. Yeah, I think I mentioned to you when we met in London that I've got a client that are trying to do this in-house. But I think something you said there is isn't there, right in saying there's an enormous amount of compute? Not only do you have to have really genius level people working on it, but isn't it the compute required to do it better than something like what you have is? Yeah, you have to be like a tech giant basically to be able to do that. Is that fair to say?
Yeah, you need to be a substantially sized company with good funding and kind of a good customer base who can kind of fund some of these initial developments. Some rough estimates is we run our individual high resolution domains over the CONUS in the United States on roughly 4,000 processors each for roughly 2 hours to generate those forecasts. So we're using, what you might call up to 50 nodes, individual nodes, which is like a substantial computer that might sit on your desk, but in the cloud. We're using roughly 50 of those for 3 hours. So costs build quite rapidly. And then the data amount is large. So dealing with these different data pipelines and efficiently getting them to customers fast, which is also critical. One thing I want to mention is because most of our client base is in the energy and commodity trading markets, speed is incredibly important. So what we do, like I said, we do start with our background before we run data assimilation is the ECMWF forecast, simply because it's the best of the best that's out there. So we take that, and the instant it comes out, we start processing it. We add our data on top of it, so our proprietary data as well as publicly available data, and then we kick off the entire pipeline so that our high resolution forecasts are produced before the next set of global runs come out. So traders kind of have additional information on top of that current ECNWF forecast before, say, the next one comes out, or the next GFS run, or the next model run that moves markets. And for Morco traders, timing is incredibly important, probably is equally as important as the actual accuracy of the model in many cases.
Yeah, no, I think so. I can't remember. I might be wrong on like accuracy, but someone was telling me, obviously Citadel have got an incredible in-house proprietary system, and that beats the market. Someone said by half an hour or something crazy like that. But that obviously the cost of that is huge, but the amount of profit that they've generated because of that is probably in the billions, which is not everyone's Citadel, but shows like the value of getting accurate weather and speed, like you say.
Yeah, so what you brought up, and I'm a little my speculation here, but I know companies do this and traders are very interested in it. This is kind of a niche area of the energy trading market. Is called front running public models.
Yeah.
So NOAA runs the GFS, that global forecasting system. That's it's not as good as the ECNWF, but it's kind of the other big player, this number 2 in the game. And NOAA open sources all their code, so you can actually take the GFS model and mimic the exact system. You also need to use the exact same compute to identically mimic it, because the errors propagate, and if you're not using the same hardware, things are computed a little differently and errors grow. So you need to completely mimic the system. It's a massive engineering problem, and there are companies out there that do this, where they take the code, bring the exact same data in, run it on the exact same compute, but run it just a little faster, so they get that 30-minute edge. So they know what the model's going to show before it shows. So that is an area that a lot of these players play in, which is completely outside the realm of creating a better forecast. It's simply just beating the market and knowing what the next publicly available data is going to show.
Yeah, no,
it's a very interesting area.
Yeah, for sure. Especially, like I say, for traders, they're looking at always trying to find an edge. That's what it's all about. And I think just another anecdotal comment that I heard recently, which is again why people are looking at weather so much when it comes to power trading, is company in the UK got a portfolio, and they were telling me that it was very rainy last week or the week before, and there was just a window of like half an hour where everyone thought it was going to rain and it didn't, and it was just cloudy. And that window to them, if they got it accurate, they said just half an hour, it was like worth like $1 million to them. It just made me think that's crazy. Half an hour's worth $1 million. Like getting it right in just short windows is obviously the numbers are massive.
Exactly. Yeah. So with all power traders are aware of this, but with increasing renewables coming online, electricity prices are getting more and more volatile, because you'll have when the sun's shining and the wind's blowing, you have tons of energy production. And like you said, if you have one massive solar farm, and even the biggest solar farms are still only the size of very small clouds, which no model can individually resolve. But if one forms and goes over that solar farm, well, you have significant drop in production, which of course creates extreme volatility, or can create significant volatility in energy prices. And that's that's an area where we're very interested in Spire, and that's why we run our high resolution forecasts. We also we have a proprietary system actually within our high resolution forecast, where we actually run a global cloud analysis at 3 kilometers, and this is developed by one of our scientists here who's really a world-renowned expert in actually the formation of clouds and modeling them. And they built a system which takes radar data from all over Europe and the United States, as well as all available satellite data, and analyzes the 3D properties of clouds. Because typically, if you don't put this into a model, it takes 6 to 12 hours for it to spin up. And that first 6 to 12 hours, your precip and cloud forecast can be very inaccurate. But we take what's actually been observed, and then we have custom code that we've developed in the model that actually triggers these clouds and storms so that they're placed in the exact right area with their exact right shape and size, so that first kind of 24 hours of the forecast is actually analyzing the clouds properly and then propagating them forward in time, which is huge for especially solar and wind, because clouds create storms, which create wind. And it's very important for our renewable customers that we really nail that short-term forecast. And beyond that, we are going to be developing what we call a nowcasting system, where it's going to be purely AI based. This is where we're going to kind of train satellite imagery, radar imagery to predict the next 6 hours. And it's going to run it very rapidly. So we'll probably run that several times per hour. And then that'll be kind of a really key product for these very kind of short-term traders on the solar energy side. But that's something we have on our roadmap that we're going to be working on next year.
Awesome. Well, that leads us on nicely to AI. Obviously, in the last 2 years, there's been some huge breakthroughs in AI, and everyone's talking about how it's going to transform lots of different industries. But what I'd be really interested in is the impact of AI when it comes to weather forecasting. Can we talk about that?
Yeah, definitely. So I'll give kind of a brief background on how AI has changed the weather prediction industry. So these models I've talked about so far, such as our high resolution model, our global model, these are all traditional, what we call physics-based models. They're still the most proven, the most reliable. They're still, 99% of the model forecasts you see out there are physics-based predictions. And it's really kind of a sort of a technical marvel of how far we've come with weather prediction. Really, the first computers were some of the first applications of computers back, I guess, close to 70 years ago now, were weather prediction. There's some really famous scientists like Lorenz and Bjerknes and people like that who kind of initially started to realize that you can actually, rather than just looking at the sky and kind of analyzing how the weather's moving, you can actually compute it because we know the equations of the atmosphere. So over the years, with the advancement of computation and the advancement of our understanding of the knowledge of the atmosphere and all the interactions it has with, say, the ocean, the land surface, and other components of the Earth system, we built up these massive code bases. We're talking that tens of thousands of lines of code, extremely complex. And yes, they're still written in Fortran, which some people may know is kind of one of the original coding languages, but nothing really beats the speed of Fortran when you're doing massive amounts of partial differential equations, which is what we do. So we take this massive equation set, we discretize it, and then they run it forward in time. And if you look, there's some great papers. There's one by ECNWF called I think it's like the silent revolution of numerical weather prediction, which just shows over the past 60 years, progress has just been perfectly linear. And it's a community effort. A lot of these models have code developed from many different research institutions, different groups. They perform a field study. They better understand how precipitation interacts with topography, and then that knowledge is transferred into the model. So we've developed these massively complex code bases that do work extremely well, but they're very expensive to run and very tough to innovate on just because of their extreme complexity. So about 4 years ago, starting in academic labs and then moving to big tech, people began to test and realize that you can just take, rather than coding up all the laws of physics of the atmosphere, you could take 50 years of data from typically use the ERA 5 data set. It's a reanalysis from ECNWF. And you can train the model. This is really simplifying things, but you can train it to just predict the next 6 hours of the truth data that actually occurred. And then if you apply this to a forecasting situation where you give it the current analysis of the atmosphere, they do a phenomenal job actually predicting the future. And not only that, but there are several orders of magnitude cheaper to run. So running inference on these AI models is pennies compared to thousands of dollars for the physical models. The speed. They produce a 10-day forecast in roughly 10 to 20 seconds, whereas it takes our current physical models hours on thousands of processor cores to produce a similar forecast. So those are really the huge advantages. It's speed and cost. And additionally, it's the time to development. You can develop, they are very expensive to train. The GPUs are in extremely high demand. So you're talking $100,000 to $1 million to train these models. But once they're trained, they're extremely easy to cheap. And companies like NVIDIA and Google, NVIDIA came out with ForecastNet, Google came out with GraphCast. have developed these models and open sourced most of them so the community can then use them and fine tune them. And they're really game changing. They have their limitations, which we can talk more about, but they also have significant advantages. And even some of the largest, best performing research institutions and modeling institutions, such as ECNWF, have now built a team around a team to focus on AI modeling. And they now have the AIFS, and then they have an ensemble system based on that. And they're really leading the way in the public sector by really bringing AI to kind of mainstream weather forecasters.
Okay, that's really interesting because I think everyone talks about what the potential of AI is, and in lots of different industries, but it's kind of more thinking in the future. Whereas it sounds like AI has already had like a transformative impact on weather forecasting today.
Yeah. Certainly, it's really interesting because a lot of all these major weather conferences you go to, such as the American Meteorological Society, which is the largest one, has the annual event, and a lot of people are kind of having an existential crisis. Like, we've built all our infrastructure around these physical models, we invest billions of dollars into improving them, and now AI has come along, and there's small startups, individual companies, individual groups like what we're doing with Spire, which I'll talk about, that are coming along. And in some cases, they're beating the performance of these massive physical models that we've spent decades and everything. So they have to change their entire way of thinking about how they're going to develop the future of weather prediction and not fall behind. So it's making significant inroads, all the way up to the funding of NOAA about how do we assure that we become or maintain our leadership in weather prediction when we're not as nimble as a lot of these kind of technical tech companies and small startups, where they can quickly, add and create these weather models and prove their benefits. So it's a very interesting time all around.
Yeah, like I can just see that myself with even in Europe, the last couple of years, the startups that I'm starting to see in this space. So yeah, like you say, it's already here. So yeah, could we go a bit deeper into that? So like, what is the impact that we're seeing in general, and where do you think it's going to go?
Yeah, so I'll talk about how we're thinking about AI at Spire. Because Spire Weather itself has been around about, I think, roughly 10 years now. And for those first, 8-9 years, we were purely focused on physical modeling because that was the best of the best. That was the way to create the best forecast, which is ultimately our goal. And then we started working with machine learning and AI a few years ago. And now we're kind of moving into the more foundational AI model development. So we've been doing post-processing machine learning, where we take our physical forecasts and we train them on truth data. And this kind of removes bias from the forecast. It allows us to understand the uncertainty of the forecast, so we can generate kind of probabilistic forecasts. And we also have now started taking our high resolution forecast and generating power curves from that. So obviously, in the energy and the trading industry, ultimately they want to know what's the expected power output from this weather forecast, whether that's wind or solar. So we're doing a lot of really innovative stuff. We have a really strong team working on that, where we're doing right now we're starting with countrywide predictions over Europe. It'll be moving over to ERCOT. Then we're ingesting many months of our high resolution data and then training it to predict power curves. This is purely data-driven models using convolutional neural networks and transformers, so very kind of modern techniques to produce the best possible power forecast. So that's kind of what you'd call on the post-processing side what we're doing. But we're now moving into the more foundational AI modeling side, and we believe the most significant benefits are actually going to be on what you call the subseasonal time frame. So this is roughly 15 to 45 days. It's considered the most challenging time frame in weather prediction, because initial conditions don't matter too much there, but seasonality hasn't totally kicked in, so it's incredibly hard area to predict the weather. And physical models have not proven too much. They're generally fairly unskillful in that area. But we believe that with AI models, it's going to be able to understand, the connections of how, the MJO, which is an area of convection, generally over near the equator, usually over kind of Southeast Asia, how that affects the weather over, say, London or the North Sea. This isn't always clear in physical models because we just don't understand all those connections. But training an AI model, it'll be able to find if there a pattern exists. Modern AI systems, with the amount of data they ingest and the type of neural network architectures they're using, they will find that pattern. So we believe there's the most skill to be gained in that 15 to 45 days. So we're working on developing our own model, which will start with, it will be using the typical kind of aerified data set, which is the best of the best. And there's not really a competitor there to train the base of the model. But then we have years of Spires. We run our own global data simulation system. So we have years of Spire data that we're then going to fine tune the model on. And then we're going to run the model with Spire data simulation as well. And that's a bit different than other providers and entities who need to rely on, say, ECNWF analyses or GFS analyses. There's only, to my knowledge, a couple other companies that actually run their own global data simulation. So we can run that at different times. We have a proprietary data in that, which is obviously, positively impacting the analysis. And then not only are we going to be running this model to 45 days, but we're going to be running it as a massive ensemble. So we're going to be running with over 250 individual members. An ensemble member is when you kind of slightly tweak either the initial conditions or the actual model itself to produce a different outcome. And with physical models, you can really, most providers max out around 50 members because they're so expensive to run the model 50 times. And you don't understand the full distribution of possible outcomes. But with AI models are extremely cheap. So we can run it many times and create massive ensembles of over 200 members. And we can really understand, what's, depending on how the members cluster, we can understand the most likely scenario, whether in that 30-day time period, we expect it to be colder or windier than normal, what kind of weather regime you're going to be in. And we also can understand the extremes a lot better. So what are the kind of the tail events, which are also obviously incredibly important for traders. And we're right in the midst of training up that model right now. We expect to be able to be launching it actually at the end of this year.
Wow. Okay. So going out to 15 days all the way to 45, that's just not possible before AI. Is that basically where we're at?
It's possible. It's possible. Yeah. And there are many models that do it. ECNWF has one, GFS has one, but there's this phrase that I can't remember right now. It's something like the valley of unpredictability or something like that that's used within the community, where it's just so hard to predict that the actual useful information in these models is very small. So we believe because there's so much to be gained in that time frame that this is where AI should be able to come in and really make a big difference. Whereas, for example, our short range models are already so strong, and there are inherent issues with some AI models with how they kind of smooth out forecasts. And, we can dig more into the details there, that we believe ultimately the most significant impact is going to be on that subseasonal time frame, which is also where traders have an area to, because forecasts are so poor and we really don't know what the weather's going to be like a month out. There's a lot to be gained there. There's a lot.
100%.
If you're a little more useful information. Yeah, a little more useful information, you can make a lot of money.
If you're trading on the curve, like having that kind of 45-day analysis that is going to be a lot more accurate. Yeah, that sounds dreamy for a curve trader.
Definitely. Yeah.
Amazing. So just picking up on something you said also. So my interpretation there is on the short term, physical is like really good. And can AI get better than the physical in the short term? Or is it more the big opportunity is in further out?
So that's a great question. So let's say there's four time scales of weather prediction. There's what's called kind of nowcasting, which is kind of 0 to 12 out, 0 to 6 even hours. So very short term. And then there's kind of the 6 to 12 up to say 5 or 6 days short term, medium range 5 to 6, 15, and then subseasonal beyond that. Right now, with the current state of things, AI, in my opinion, this is sort of my opinion, is best suited for that long range, like we talked about, the 15 to 45 days. And that nowcasting phase. So the 0 to 6 hours, it's very hard to gather all the data, spin up your physical models, and have them produce rapid forecasts. And Google's actually done a lot of great work on this, where they've just taken years of radar data. They call it the MetNet model, and they've trained it. They just predict the next radar frame, and that kind of informs you where precipitation is going to be moving in the future. And the model actually learns to kind of dissipate and grow individual precipitation kind of convective cells, which is really fascinating. Before, typical nowcasting models will just use what's called kind of an optical flow method. Getting a little technical here, but that's just where you kind of advect the cells forward in time. So there's been a lot of promise on that extremely short range. And you can imagine creating a very strong cloud forecast where you're using sort of visible satellite data all around the globe. So you know where clouds are at very high resolution, and then predicting the next frame of where that's going to be. So it's sort of a video prediction problem, which is largely been solved in the AI community, but you can apply that to weather data. So you can apply that video prediction model to either radar data or any sort of visible spatial satellite data set. And I've seen some very promising research where using, for example, diffusion models, which are commonly used for video prediction. You can predict the next frame of a satellite image and know where clouds are going to go and where they're going to form. And because they're so cheap, you can run them, say, every 10 minutes. So you're just getting this rapidly updating model that provides really reliable information. That simply cannot be done with the physical model. But yeah, and like you said, in the short term range, which we kind of call the 6 to 12 hours out to 5 to 6 days, that's where resolving the true physics of the atmosphere at very high resolution, it's very hard to beat that with AI. And a lot of that has to do with, we just don't have strong three-dimensional analyses that know the historical weather going back 50 years to actually train these models. There's been some promising work kind of taking a global forecast and downscaling it to 3 kilometers, but you're missing a lot of information there about how the small scale weather actually influences the larger scale, because they're just downscaling. You're just going from large scale to high scale to small scale, sorry. So if the global model missed the placement of an individual low pressure system, it's still going to be in that place. The high resolution data is not going to be able to impact it.
Okay. That's the current state of play. Would you think it will get there in the future, or unsure?
I believe so. I think there's so much innovation happening in the AI space. And if I just think about, where's the innovation usually comes from? A lot of times it's kind of the grad student has an idea, they're allowed to explore something new. And every kind of younger person these days, they're not looking to kind of dig into these old traditional physical models that are very hard to innovate on. They want to use data-driven techniques and AI. And, there's more and more compute for AI. There's more and more data. But I think a lot of these challenges are going to be solved. So I think, my opinion is 5+ years from now, a lot of what we do is going to be purely AI driven in the weather space. And I want to mention that right now, what we're doing in the AI, what's working right now is really sort of a hybrid technique, because we still use these physical models to run our data simulation systems. To bring in that raw satellite data and create a gridded analysis, that's using physical relationships similar to what's in our numerical weather prediction models. And then by training on those, the AI model actually just learns the physics encoded in the data simulation. So it's not a pure data in, data out method, but there's a lot of research going on into that where you skip the data simulation component. You just take all the satellite data, all the weather stations, all the data from aircraft and balloons, and you train this massive AI model that directly ingests the raw data and then makes a weather forecast. And that's where I think we're going. There's a lot of large efforts in that area. It's very exciting and may cause a lot of people a lot of anxiety if that happens, because it's going to really reshape the whole industry and the public sector as well.
How so?
Just because we've invested, it's just different. The weather, up until about 10 years ago, weather prediction was completely managed by public sectors. It's just too expensive an investment to launch your own satellites, get your own data, have enough compute to actually run these models. And it's really only in the last 10 years that kind of industry players have begun running their own models, generating their own products that are, providing additional value. And so governments are built for these traditional pipelines of data simulation, building these large physical models that are extremely expensive. And I think they really need to, and there's tons of expertise in that area. And if it turns out that we don't need to, there's always a need for basic research. I think a lot of findings always come out of that, so we should always continue that. But if we don't need to be running these huge physical models and these data simulation systems, it's going to really reshape how we distribute funding, what kind of we focus on, and things like that. And I think that the public sector is, like I said, it's much more nimble. They can rapidly adjust. They can figure out, they're going to test out these models. They don't have the risk on their hands. They can do it a lot more cheaper. I think they're going to be able to innovate much quicker in this new paradigm. Some people think this is going to happen in 2 years. That's not my opinion. I think it's going to take time, especially for people to gain confidence. I think we're looking at more 5 to 10 years down the road when these pure data in, data out models really start to take hold. And one thing to know is when we go towards these pure data in, data out models, it's the data is going to become even more and more important, because you don't have the physical relationships within the AI models need to be learned from the data. And we have huge data sparse regions over the world. So additional satellite data, like some of the work that Spire is doing. And I also want to mention that Spire is going to be launching its first hyperspectral microwave sounder next year. And we plan to eventually build out a constellation of that. That's kind of our future data set, which provides a lot more data than RO and goes all the way to the surface. So that's kind of phase 2 of Spire weather on the satellite side, is building out that constellation of data. I think there's going to be more and more demand just for more data, because you need to still understand this current state of the atmosphere to produce even a better AI forecast.
So certainly a very exciting time right now. And it's good to see like a real example of how AI is like changing like an industry like right now. because like I said, there's a few that are, it's kind of up in the air and predictions, but we're not seeing it already. But look, I've got a question from someone who works in the industry, so I thought it'd be good to ask. And you may have covered it already, but just want to ask. So they want to know: are you focused on foundational or post-process AI for forecasting?
Yeah, it's a great question. And we are doing both. So I kind of mentioned this, but perhaps it wasn't completely clear
Yeah,
addressing this question. But we do the post processing kind of machine learning AI, and that's where we take our physical forecasts and we train it,
yeah,
the output of our actual forecast data, and train it on truth data. And this kind of removes
yeah,
bias and allows us to create a better, say, wind forecast or temperature forecast, and also gives us an indicator of the uncertainty in our forecast. So we can create kind of probabilistic
yeah,
forecast based off that. We also use machine learning post processing to generate our power curves. So we take all the output from our high
yeah,
resolution models, and we're going to be expanding that to other models. And then we generate, power estimates over, for say, wind production over Germany or solar production over France. We're doing that right now with AI. And on the foundational side, that's where we're building this sub-seasonal AI model. That's, there's no physical model, no physical numerical weather prediction model in the loop there.
yeah,
It's going to be AI is replacing it as the
yeah,
foundation of the actual prediction component. And then the raw output is used to generate kind of different sorts of forecasts, such as weather regimes. You will have the raw data in that forecast, such as 2-meter temperature,
yeah,
10-meter winds, things like that. But we'll also kind of distill it down into information that's useful for traders, like what is the general weather pattern going to be over Europe in that time frame. Obviously, you're not going to know exactly what the weather is going to be over London in 30 days from now, but
yeah,
you get a general sense. Is it going to be cloudier than normal, colder than normal,
yeah,
windier than normal, et cetera? And that's what's useful at that time range.
yeah. And it's getting more accurate, like you say, with that further out. Cool. And let's say there is a trading company who are like, oh, we want to have an edge. Is there any way that they can be like coming up with a customized solution with Spire?
Yeah, so we have kind of our core foundational forecasts, you could call them, on the physical
Yeah,
side, and we're developing one on the AI side. And that's kind of what, runs our entire business, or our weather business, at least. That's the core of
yeah,
our weather business. And
yeah,
that data then goes into several products. We have visual display systems. So we plot all our data with tools to easily kind of, instead of having to get the raw data from an API feed, you can actually just visually look at it. And this is useful
yeah,
for a lot of forecasters. Get quick looks and compare our runs to ECWF runs and other things like that. And so we host all of our data in a very easy visual format. We also host, you can access all the raw data from our models via an API, and you can integrate it into your own systems and into whatever kind of systems you use for trading of electricity. And we do also work with customers and do a lot of kind of custom solutions. So we run our high resolution models over Europe and the continental United States right now, but we are working with other customers to do kind of custom domains because we can expand the system anywhere in the globe. So we have some domains we're talking about kind of over Southeast Asia. We have some we're looking at over Mexico in South America for other traders. So that's something we can do on a kind of a customer by customer basis. And then on the power curve side, we're working with various customers to expand those to either other large regions such as ERCOT or other areas of the United States. And we plan to
yeah,
even go down to kind of point locations, so individual wind farms. And that's something where we might work with a customer who has a wind
yeah,
farm and they have data that we
yeah.
want to train into the model. And we definitely do that. So we have our
Okay.
foundational part, we have our core products, but we also have a kind of a custom solution side of the
Yeah.
business.
Yeah. I was thinking, yeah, if you had a specific win part, that would be like super, super valuable, wouldn't it?
Yeah, we do that. So we have another product that's our point optimized solution. So rather than getting a gridded spatial output, you get
Yeah.
precise weather data at one point. And we do
Yeah.
work with some customers to actually integrate their own sensor data into that. So we train the model to get even more accurate forecasts just for their individual location and data that they have
Mate,
internally.
amazing. Amazing. So yeah, if you are a trading company that is focused on power trading, wants more accurate weather forecasting or has a asset portfolio and wants to talk about that specific product, we should get in touch with you then, Tom. Is that right? Then you can introduce them to the to the team.
Yeah, definitely reach out to me and we'll get other people from the team involved, and happy to work with you and find kind of solutions that can produce better weather forecasts and ultimately save your assets and generate more revenue, protect
Yeah.
your assets and generate more revenue.
Amazing. Well, look, that was a really interesting chat, Tom. I personally learned a lot. I'm sure others did too. So yeah, appreciate your time. Thanks a lot.
Yeah, no problem. Thank you, Patrick. Enjoyed it a lot.
Cheers.